When you look up at the night sky, there's one thing that's always there, right? The moon. It just feels permanent. Like it's been there forever and it always will be.
It's this constant presence, watching over all of human history. We just assume it's this settled, balanced part of our world, a perfect celestial dance that never ever changes.
But what if that's all wrong? What if that feeling of a constant companion is just an illusion? Well, here's the mind-bending truth. Our moon is actually escaping. Slowly but surely, it's drifting away. And the reason why is all down to the relentless laws of physics. So let's dive into this cosmic mystery. Okay, so first things first, how on earth do we even know this is happening? I mean, it's not like you can just look up and see it, right? Well, it all comes down to some seriously precise science and a few souvenirs the Apollo astronauts left behind. So get this, the moon is moving away from us at about 3.8 centimeters a year. To give you some perspective, that's about the same speed your fingernails grow. Now I know that sounds like nothing, right? But when you're talking about billions of years, oh, it adds up. It adds up to a huge shift. The absolute, undeniable proof, it comes from something called the Lunar Laser Ranging Experiment. You see, back in the day, the Apollo astronauts and the Soviet Lunokhod rovers left these special mirrors called retroreflectors sitting right on the lunar surface. And for more than half a century now, scientists on Earth have been zapping those mirrors with powerful lasers. They measure the time it takes for the light to travel to the moon and back, which is a zippy 2.5 seconds. This lets them calculate the distance with millimeter accuracy. And after decades of doing this, the data is crystal clear. The moon is, without a doubt, drifting away.
But here's the thing. This isn't something that just started happening. The evidence for this long goodbye is literally written in the rocks of our own planet. The clues have been waiting here for billions of years.
And what's really wild is just how far the moon has traveled. Right after it formed, it was so close to Earth, maybe only 20,000 kilometers away. Geologists can actually see the proof in ancient rocks called tidal rhythmites. They're like fossilized records of ancient tides. We can even look at fossil corals, and their growth rings tell us that millions of years ago, a year had way more days because each day was much, much shorter. And that's the other half of this cosmic equation. As the moon drifts away, the Earth's spin slows down. These two things are completely connected. Think about it. Back when the moon was super close, a day on Earth might have been only 6 hours long. That 24-hour day we take for granted, yeah, that's a direct consequence of the moon's slow escape. Okay, so we know that it's happening, and we have evidence it's been happening for a very long time. The big question is, why? Well, the answer lies in this incredible gravitational tug-of-war playing out right here in our planet's oceans. It's a process called tidal friction, and really, it all boils down to a simple transfer of energy. Think of it this way. The Earth is losing a little bit of its spin energy, and that energy has to go somewhere. Well, it gets transferred to the moon, giving it a little push into a higher orbit. So here's how it breaks down. The moon's gravity pulls on our oceans, creating those high and low tides, right? These are the tidal bulges. But here's the catch. The Earth rotates way faster than the moon orbits us. So our planet's spin literally drags that tidal bulge of water slightly ahead of the moon. And that bulge of water has its own gravity, which pulls the moon forward, kind of giving it a speed boost. That boost pushes the moon into a higher, more distant orbit. And in this exchange, the Earth's spin slows down, just a tiny bit. It's a perfect trade-off. So this whole cosmic dance has had huge consequences for Earth in the past, and it's going to have some pretty major ones for our future, too. I mean, it's pretty simple. As the moon gets farther away, it's going to look smaller in our sky. It's a really slow process, of course, but it's happening. And this is going to have a really kind of sad consequence for one of the most amazing sights in nature. Right now, today, we live in this incredibly special cosmic moment. It's just a coincidence that the moon appears to be the exact same size as the sun from our perspective, allowing for perfect total solar eclipses. But in about 600 million years, the moon will have drifted so far away that it'll be too small to completely block out the sun. Future generations on Earth, they'll only ever see what are called annular eclipses, those ring of fire ones. The breathtaking magic of a total solar eclipse, it's going to be a thing of the past.
And believe it or not, the moon's job is so much bigger than just eclipses. Its gravity is like a giant anchor for our planet. It holds our axis steady at that 23.5-degree tilt, which is what gives us stable, predictable seasons. Without our big moon, Earth's axis would wobble all over the place, kind of like Mars does. And that would mean absolutely wild, chaotic climate swings. We owe our stable climate to the moon.
So, what's the endgame here? Does the moon just keep drifting away forever? Well, physics predicts that eventually they'll settle into a final stable dance. But there's a huge cosmic twist to this story.
See, if you let this play out for, say, 50 billion years, the Earth would eventually slow down so much that its day would be the same length as the moon's orbit. They'd become tidally locked to each other. The moon would just hang motionless over one spot on Earth, a permanent moon for one side of the planet. But there's a problem. Something else is going to happen way, way sooner.
Yeah, that final stable dance, it's almost certainly never going to happen. Because long before that 50 billion year mark, in about 5 billion years, our own sun is going to run out of fuel and swell into a red giant. It'll likely swallow the inner planets, including Earth, completely changing or ending the whole system.
And really, that's the big takeaway here. The universe isn't static. The night sky isn't a fixed painting. It's a dynamic, living system that's constantly changing. So the next time you look up at the moon, just remember, you're not just looking at a big rock reflecting sunlight. You're witnessing a snapshot of a relationship that's billions of years in the making, and a dance that is still, very slowly, unfolding.